Well, you have discrete sources like this, one by one, more like an antenna array. So if you take my antenna class, then you understand that this is more like an antenna array. But as the fill up the space, so you have one line, so now it becomes more like a single antenna in space. Okay, so that's again do the superposition calculation. You have a antenna like this. You have done this calculation before in the antenna class, right? And then you calculate the optical path difference at every point relative to the center of the antenna. And then you specify, of course, the wavelength associated with it. So this is a standard calculation you learn from the antenna class. 还记得吗? Right. So you have one antenna, and then you calculate the current on this, producing radiation here, and then you do a coherent sum for every small section of it. And then, of course, you want to calculate the optical path difference, the path difference between this antenna, this emitter, and the reference the point on this antenna. All right, so looking into this geometry, this triangle, then you can express Ri as a function of R given a Y position. So this is triangle, you have this relationship. Simple and easy, right? Okay? Have you done this calculation before for a triangle given this angle? This angle is 90 degrees minus theta. Okay, so for this triangle, R squared plus Y squared minus 2RY cosine this angle is the square of this length. Do you recall some memory in your brain?
I can understand it.
Yeah, you try to calculate this path, right, as a function of this and this. You get this. All right, so now we talk about far field interference. In the front half diffraction, the R much larger than the antenna. We did this calculation exactly when we talk about antenna in the electromagnetic wave. This R is much larger than the size of this antenna. This antenna is like this, but we're picking up signal 1 kilometer away. So this R is much larger than 1. So you do a Taylor expansion. You do a Taylor expansion, divide the whole thing with R to get this zero order term, first order term, and second order term.
We treat it like a point source.
Yeah, we treat this as a line, but very far away. Very far away. So we keep the first order term. Okay.
Can we not treat this as a point source since you're talking about?
No, there's a final length associated with it. So if we treat as a point source, then we take out all the high order term. But you compromise a little bit and recognize that the first order term will still contribute to the phase of the interference. So you don't do that. You don't do it very aggressively. Okay. If you do it very aggressively, then you would need to deal with this expression. And this is the so-called Fresnel diffraction regime. But then you expand it into first order term, second order term, third order term, and throw away the second order term and higher order term, and we call it front half diffraction. Don't treat it as a point source yet, because with a finite length, this term still contributes to the calculation. Okay. And we did this calculation exactly the way we talked about antenna before. Well, initially we talked about Hertzian dipole. We treat it as a point source. And then we start to talk about linear antenna. And so we take into account the finite length of it, right? And we do this calculation, session point by point. All right. So remove this higher order term. Just keep the first order term, and then you do this the coherent sum calculation. Exactly the same as you did for the antenna calculation. You can remember this, right? So now you every point produce a wave propagating along R direction, but this R is approximated by this first order term. Okay, I repeat this a few times that we did this calculation for a linear antenna exactly. Okay. All right. So if you integrate the over the whole antenna between minus D and 2D. Okay. Because some of you were in my antenna class, let me bring up this linear antenna calculation. Right, this is something that looks familiar to you. We talk about antenna with a final length. With a final length, and then there's a length between minus H and H. Okay. And then how do we do the calculation? Well, we model it as a dipole antenna. That is the point source. Right. So we chop the antenna into small section. What do we do? We chop it into small section, and then there's a certain wave emitting from this point source, and then do an integration between minus H and H. Right, we do an integration over this, and then basically we just take a section of this and model is the point source. And then we calculate this R prime relative to this R. Okay, and then you see the linearization of this calculation, because the high order terms are taken away. So you have this linearized relationship between R and R prime. All right? And we are doing the same thing, exactly the same thing, between R and between this small r. Previously on the last page, this is R prime, this is R. We have linearization. Whether this is sine or cosine depends on the angle I define. I define this theta angle to be between R and this normal axis. So previously, the angle was defined here, so you get a cosine dependence. Okay, so this is exactly the same calculation we did for the antenna class. And so finish up this calculation, you end up having this result. And this result is exactly the same as the antenna, linear antenna radiation field. Okay. So you see a wave propagating away, and then there's a certain antenna pattern function. This antenna pattern function. Right. And I want to point to you something that is quite remarkable in this calculation. Because this will connect to later more elaborating calculation for Fraunhofer diffraction. Let's decompose this into complex notation. This is the same as this. If I just decompose this sign into this complex notation, you recognize this is the Fourier transform. What is Fourier transform? Fourier transform is some function of t exponential minus I omega t. This is Fourier transform. Each are all agree? Yes. Yeah, everybody recognize it. Each and agree. This is Fourier transform. Okay. Let's change this t to space. Just change it to y. So in this expression, it's omega. So change it to k sine theta. Or here k sine theta. And this t change to y. That's it. You shall recognize it. Should I? This is Fourier transform, do you agree? Okay, you integrate over time. Let's change the variable from t to y. And omega to k sine theta. And integrate from minus infinity to infinity, you have the average function. So now this is a rectangular function. Y over b. Are you familiar with rectangular function?
Yes.
Zero and y larger than equal to 2. 1/2 y equal to 0 to 2 and 1 over y less than 0. This is the rectangular function. Okay. So basically, if you plot the y, this means that you have unit amplitude 0 equal to minus equal to the unit amplitude. So this is rectangular function.
Why is it 1 by 2 t by 2? Is it not 1? Should it not be 1?
No. Right at the center, this value at the boundary is 1/2. So this is a rectangular function. So this, in this expression, is a rectangular function like this. So you integrate from minus d over 2 to 0 to 2. All right. So the point I want to give you is that this calculation, in fact, is a Fourier transform of this aperture function. Okay. The result is a Fourier transform of this aperture function. So in front of diffraction, you're going to see that if you have some average here, and then you want to know the far field diffraction pattern, then you do a Fourier transform of this aperture function, just like this. So now you recognize a very simple fact that I did this interference pattern. Not so easy to do experiments. The field pattern you see on the wall this time is not so okay. The field pattern you see on the wall here is a Fourier transform of my slits. So it's a sinc function. This is the rectangular function. All right. So you get the point. So a lot of things could be very simple in the conclusion. Okay. And this is the beauty of the physics. You went through the physics and then start to realize that hey, the design of this world can be just very straightforward. All right, so we end up having this. In fact, it's a first transform of this the rectangular function. So it's a sinc function. And in this class, sine A over A is defined to be sinc A. It's the people call this unnormalized sinc function. Okay. But in some definition, you have pi in some definition you have sine pi A over pi A equal to sinc A. And this is called normalized sinc function. We don't do this. Okay, in this class we will adopt this. Okay, so this is a sinc function of the same argument. Okay, all right. So you see a sinc function in the far field when I project a slit to the wall. And the intensity is like this. So you have a sinc function. This is sinc beta, and beta is given by this expression. Okay. And so this is exactly what is showed on the wall. Simple enough, right? Yeah, you get the sinc function. That is a Fourier transform of a square function, rectangular function. All right, is there any questions for this? One more question, let's make it a little bit more complicated. Now we have two slits. And then, how would you expect before you do the calculation? Don't always go to the calculation right away. Try to understand the physics. This is going to produce a sinc function on the wall. Do you agree? This alone will produce a sinc function on the wall. This will also produce a sinc function on the wall. And they will interfere with each other. Agree? All right. Because Yushan and also the Li Xiaolong were in my class. So let's go to antenna calculation. We did this calculation. Two antenna right here. How did we do this calculation? We finished calculation for one antenna. And then we add them together with some path difference. Then we end up having a result. That is given by the multiplication of two terms. One is the element factor, the other is array factor. Array factor tells you the interference of the two antenna. Element factor is the antenna pattern of single antenna. Right? So this term tells you the interference. This term tells you the antenna pattern for a single element. Right. So you have this term and this term together. This is the interference term. This is the antenna pattern of a single element. Li Xiaolong, do you recall this? Yeah. Right. So these two terms multiply together. So you'll be expecting the same thing here. You have two antennas. So you add them together. This is one antenna, and the other antenna separated over distance give you a phase difference between these two, and they interfere with each other. So you end up having two terms. Okay, if you finish the calculation, then you end up having two terms. One is the antenna pattern for a single antenna. This is interference terms. Okay, so there's no magic. This is a sinc function we just had from the single slit. And this is the tells you the interference. And of course the interference is relevant to the separation of these two antenna. Shukai can, because you were not in my antenna class. Is this difficult for you?
I think it takes some time to understand.
Okay, but intuitively, you should be clear, right? For this, you have some sync function on the wall. For this, take out this, you have another sync function on the wall. And if you open this two, you overlap these two sync functions. But you will have interference from the field, right? So the interference term is cosine alpha. We did the two beam interference before. And this cosine alpha, right? Two beam interference, we did the calculation first. And we have two sources.
So,
Previously, you have E0 plus E0 exponential minus alpha I. You have two beam interference. If you finish this calculation, something like this. Square. We did the two beam interference calculation before. And this is the phase between these two terms. That could be 1/2 or something.
so that one slit is acting like the rectangular function. Is that
Yeah.
right?
Yes. So you just you have two rectangular functions separated by a phase. You do Fourier transform here. You do a second Fourier transform here. But you can add them together to do the Fourier transform, but you need to take into account the phase difference.
Fourier transform of rect function is same.
I'm sorry?
The Fourier transform of rect function is same.
Right, but then this is a field, so you need to add the phase difference between these two. But in this calculation, in this Fourier transform, in this Fourier transform is phase sensitive. So the next rectangular function will add additional phase right here because they are separated in space. And then you add them together. Okay. And so you need to add this interference phase. This is from one antenna, the other is from the second antenna. And because they are spatially separated, so there's an additional phase. And when you calculate the intensity, then you do a square to the result. You do a square to this result, so only these two terms will survive. Okay, so if you do a square, if I do a square to this, then I end up having this very clean function. If I do a square here, I end up having this antenna pattern, element factor, and array factor right here. And this comes from the interference of the two patterns. And now, it's time for me to do experiment for you. I always want to do experiment for you so that you see something you can remember throughout your life. It's a single slit refraction, beautiful sync function. You shall only like it.
Yes.
Beautiful, right? Right. What if I open up the slits? What if I increase the slit size? You see the central lobe will become smaller or bigger. This is the first slit. This is the first slit. And then now I increase the opening size of the slit.
Shrinks.
Becomes smaller. Okay. In fact, we can see from the formula. When you increase the when you increase the slits, when you increase, what is the beta? This, when you increase this, when you increase this, you increase this, and then the width becomes smaller, because this corresponds to beta equal to pi for certain beta value. So if you increase this, you reduce this. When you reduce this, you increase this. This point is a constant beta equal to pi. Got it? This point is when beta equal to pi. So this is the width. This corresponds to certain value of this pi. This is pi. We'll go to this point because sine beta pi equal to 0. Which are we got it? This sine beta pi, sine pi equal to 0, right? 0 divided by pi is also 0. Correspond to this point. All right. So this half width is pi. So if we increase this set is equal to pi. When you increase this, you reduce this theta. When you reduce this theta, it becomes smaller.
That's why in my signals and systems class it says that expansion in one domain is contraction in another domain.
Right.
That's how we.
So if I reduce the width, it becomes wider at the center. Okay, this is the wide slit, and then this is the narrow slit.
And it's not that clear from here, but it's the same function that is being.
Yes. So what you are seeing is a sinc function. This is a sinc function. Do you agree? This is a sinc function. You are seeing those side lobes. Okay. So this is a sinc function.
It's very clear in the picture.
Yeah, very nice, right? All right. Then I'm going to give you two slits. I'm going to give you two slits. See what happened on the wall. Wow, this two slits. Diffraction. Beautiful. Two slit diffraction. Okay, and this is exactly you're seeing right here. So interference of the two slits. Right? You're welcome to take a photo for yourself because this is quite obvious. We fabricated this slits in our clean room and just try to illustrate this to you. So from my point of view, this class is valuable in the sense that we understand everything from your eyes. All right.
And the dark ones are the zero crossover.
You see
Okay.
those? You see some side lobe. You see small dots, even in this sinc function. Ooh, you see this? You see the modulation of the intensity, small dots and big dots. Compare this with the figure on the slides.
And how do you generate this diffraction? Are you using your fingers or?
No. That's a slit. We fabricate this in the clean room. Yes, you see three slits. But you cannot see it from. You see single slit and double slit. Two are single slits. One is double slit. Yeah.
Thank you.
So this is the. You have to take a look.
I studied this first in my class 12 about Huygens double slit experiment.
Okay, Young's two slits.
Yeah, Young's double slit experiment. And then this is the first time I'm seeing the slit.
It's real.
Yeah.
That's real. But in fact, anybody can just use a finger to do a single slit experiment. Ooh, this single function. I just need to have a stable hands.
Because this one gives a pretty clear picture of.
Right. So that's super. This is the fun of learning, and unfortunately, in other classes, our students are not so keen to learn SFPD. Yeah. But anyway, in fact, I have another greeting that I can show you right now. Take a look at how beautiful this is. This is grating, amazing. This is grating. And then I can change the reference. You can tell me the separation of the two dots. You see some faint point, but you can see the separation of the red dot is larger or smaller compared with the green laser. You see 3 dots at least on the wall. Can you see it?
Yes.
3 dots, right? All right. And then this is. Can you tell the separation between the red dot and green dot? Which separation is smaller? This is green dot.
This one is bigger, the green one is bigger.
Okay, let me do it. And do a recolor.
Okay, no, the red one is bigger.
Yeah, the red one gets bigger. Diffraction angle.
This is
Longer wavelength. With a longer, so a longer wavelength radiation gives you more diffraction. Remember, right? Like a radio wave will give you big diffraction. An optic wave can be concentrated in some small angle. Right. So you see something. So for sure that you remember a lot of things. So I'm sort of not rushing through the materials. Just try to help us to understand the materials. Right. So this is it. You have 2 terms. One corresponding to the interference, and one corresponding to the single slit diffraction. Okay, and alpha. Don't forget that the alpha has angle dependence, and then beta also has an angle dependence. And then you see that the diffraction angle is relevant to the slit opening and also the separation of the slit. While the interference is relevant to the separation of these 2 antennae. A is the separation of these 2 antennae. Okay, it gives you the interference effect. And this B is the width of the slits. That gives you the diffraction pattern. So this term is responsible for the diffraction. This term is responsible for the interference. Okay, so this is sort of 2 slit interference. Now we could increase the number of slits to many slits. Why not? The same calculation. The same concept. The calculation is a little bit more complicated. But then you will be expecting again 1 element factor, the other interference factor, the array factor. The same as the antenna calculation. So if we go back to the antenna class, okay, then let's go to antenna array 1, 2, 3. It's just like a grating. Come on. So when you finish the calculation, how would you get? You get element factor, array factor. And the array factor you went through give you this function. The same calculation. So this class is easy if you went through the antenna theory. So specifically what you get is like this from the array factor. Okay, this is an array factor. So we talk about array, give you enhancement along some direction. You get enhancement along some direction. Okay, but then you multiply it with the element factor. So this also talk about array factor. You get enhancement along some direction. But then the whole thing will be multiplied with the antenna pattern of the element factor. Okay. So let's come back. For this calculation, the element factor is a single slit, the same function you saw on the wall. And then you have interference from all those slits. So let's do the calculation. You see this. Again, this is the same function. What is this? The single slit diffraction you saw on the wall. And this, you just saw it. This is from sine n phi sine phi. Let's go back to the antenna. Right here. Sine n phi sine phi. Right? This is the array factor from the interference of all the antennas. Now we just change the notation to alpha. Okay, we change the notation to alpha. That's it. And here we use C. This we change the notation to alpha. That's it. Same thing. All right. So it's always good that you learn something and then make a connection to what you learned before, because everything will be the same. So now you start to come back to this. Well, this term is easy. This term is just a sinc function. This term is just a sinc function. And what is this term? This term is a fast oscillation term divided by a slow variation term. And then you select some peak when this is 0 divided by 0. You get this peak. And this sinc function, wow, it's just give you an envelope like this. So this sinc function, because B is quite small compared with A, this is a slit width. B is a slit width. A is a separation between two slits. So of course, this is smaller than this. So it's a relatively slow variation when you plot a sinc function. It just gives you this envelope. Okay. It gives you this envelope. This is over here is the angle. This is the angle. Okay. So if we do it again, first ignore this because this is quite slow. Over this angle, this is small. So if you want to give a big change on, you need to give a big change on theta to get some value, right? So we first take this out and look at this. This n, if this n is big, this means it's oscillating like crazy. And then you don't have n here, so it's a slow varying term. And you divide these two together, you get this occasion enhancement when you have something divided by 0. Okay? When you have something divided by 0, then you get a big enhancement, like this, like this. All right, then let's put this slow varying term into this calculation. You basically just multiply with the same function, with the envelope. So you modulate the pattern a little bit. Should I edit this okay? So very easy to understand, right? And right at this 0 divided by 0, you get n squared enhancement right here. That is right at the center. And then that is because the principal maxima occurs when this guy is equal to 0. When you divide something with 0, you get n squared. And then between 0 and pi, when alpha between 0 and pi, between this, you have small zeros. Because you have rather small zeros here. You have rather zeros here. When you divide the zeros with something, you will still be 0, 0, 0, 0. Okay? Can you see it? You have another 0 here. When you divide the 0 with something, you still have 0. Okay. So those zeros correspond to this alpha value equal to those numbers. That is when this guy when this sign n alpha is equal to 0. Okay, and this alpha value will be equal to, for example, pi divided by n, and 2 pi divided by n, and so on, plus minus. When this guy equal to 0, then you will have those zeros here, except at this point, because at this point you divide the whole thing divided by 0. 0 divided by 0. Okay, so you get enhancement here. Okay, so that's how you generate this pattern. Divide this with this, and only this point will jump up, but then all other point will be like this. So this is the diffraction gradient. Okay. Well, I think I'm going to give you some homework assignment pretty soon, so you can practice a little bit. Okay. All right. With this, you see a lot of resonances at certain wavelengths. So this means that I can use it as an instrument. So next time on this Wednesday, we're going to use this piece of element as an instrument for measuring wavelengths, for example. So epsilon can be used to measure the wavelength of the laser. This piece of grating can also be used to measure the wavelength of the laser. And this is the opening door to give you the resolution, just like an epsilon. Okay, the width of this tells you how good you can select the wavelength or radiation when you deal with this measurement. Okay, the same concept. You can use a piece of epsilon. Remember that we have epsilon for measuring the wavelengths, but then we can also use a piece of gradient to measure the wavelengths. So, so now I can remind yourself why. Well, look at this. Look at this. You have those multiple peaks. That is the same as this. To make a comparison, the brightest one corresponds to this one. When theta is equal to 0. When theta is equal to 0, you get full enhancement. And then, because of the finite width of the slit, then you start to have suppression of the side lobes. Okay. Do you need to use this to do experiment? No, not necessary. In the old time, when people use this, it's very cheap. And in fact, on this, you have lots of dots on this. So if you send your laser onto this, what would you see? Wow. You see diffractions of the from this CD-ROM. You see the enhancement of the okay. So that is because you have arrays of apertures on this, and that is why you see a lot of different wavelengths. You separate the white light into colorful lights, because different wavelengths will have constructed interference along different direction. Okay, and that's why you see the different colors along different angle from this. You see it, right? You see the white light is decomposing into a lot of different colors, because different colors, different wavelengths will have constructed interference along different direction. So you send the laser on this, you see the grating interference generated from the array of the dots on this form. All right, so you see everything, and then the rest is that you need to go back and go through the calculation by yourself, and then you know all the details about the materials. I'll see you on Wednesday. And I hope that